Yeah, thank you, Gautier. Thank you very much for inviting us and organizing this group. I'm here accompanied by Olav from Causality, who is the main author of the paper that we will discuss today. And I'll kindly ask you, Olav, to share the screen because I'm on hotspot today and I have internet at home. So the bandwidth is quite limited, and ask also to flip the slides as well for me. That would be great.
For now, Alex, the sharing is disabled. Host disabled participant.
Gautier, can you help us? Yeah.
See that to make you wait a minute, or maybe Sam can do it. Let me check 2 minutes. Okay, Sam is telling me that it should be good now. Olav, if you can retry.
Absolutely.
Okay, perfectly. It works on the side.
All right.
Okay, thanks, Olav. I know it's early morning for you in California, so it's 4 a.m. So thank you for support.
Oh, thank you very much for waking up that early. Appreciate it.
Yeah. Okay. Let me give you a little bit of background of the work that we've done, and you might have heard this word causality a lot. And even in basic statistic books, you learn that correlation does not imply causation, and the two concepts are quite distinct. And while it's easy to define correlation, you have different formula to do so. It's very tricky to define causality. It's been something debated for hundreds of years already, starting with David Hume in 1700s. So it's a long concept, and there is even a say, I would prefer to discover one causal law rather than be king of Persia. I don't know who said it, but must be a wise person. Why is it so tricky, and why is it so important? Olav, could you next slide, please? Yeah. We always, in any domain, I'll focus the talk together with Olav on the financial domain in economics, but even in physics, in any other scientific domain, or maybe medical diagnosis, it's always useful to think about causes and effects. And speaking about causes and effects, what is the mechanism? What are the causes? What are the mechanisms that generate certain effects? And also in medicine now, in COVID-19 trials, of course, you're trying to determine the causality, whether a vaccine is effective or not. And of course, there's some standard techniques like double-blind experiments. They've been around for many decades, but sometimes in physical systems, in finance, in economics, we don't have the luxury of being able to create these causal experiments. So this is why we need to figure another way. And why we need to figure another way, because if we are a central bank, for example, or a government, we want to plan what's going to happen in the economy. We have some policy tools. For example, central banks, they have the interest rates is a policy tool. They want to know if they raise rates, what is going to happen in the economy. So always economists think in terms of causes and effects. Next slide, Olav, please. In causality, there is a certain directionality, which is not always temporal, but having events order on a temporal scale, of course, helps determining causality. I'll give some examples in finance, which are quite asymmetrical. So they're really quite prone to be expressed as a cause and effect. For example, a crash of the S&P 500 almost surely will cause the implied volatilities, the VIX index, to spike. Okay, this is a rule, but it's not necessarily true the other way around. If the VIX index has just spiked up, not necessarily there has been an S&P 500 crash. Again, central bank rates, they have impact on inflation, but not the other way around. Maybe long term, of course, when a central bank decides whether to raise rates, they look on the long-term outlook of inflation. But if there is an intervention in the markets raising interest rates, of course, we're expecting inflation to go down. And also in stock markets, mergers and acquisitions, they have impact on the stock price, not the other way around. So these are causes and effects. But what we'll be discussing today and what has been the industry settled for is a probabilistic account of causality. Okay, so if the central bank raises the base rate, they will tame inflation, but with a certain probability. So these are not necessary conjunctions of events. So if they raise rates, 100% inflation will go down. So we'll be speaking about probabilities, and we will be speaking also about uncertainty. So we can embed uncertainty through probabilistic accounts in these models. So this doesn't mean that if something happens necessarily, this leads to other things happening, but we always speak about probabilities. Next slide, Olav. So what are the tools used to model causality? Bayesian networks, they've been around for quite some time. For 30 years, Judea Puro is one of the pioneers of Bayesian networks with his seminal book that I have here on my shelf called Causality. They are part of the greater field of probabilistic graphical models, and probabilistic graphical models include Markov random fields, chain graphs, conditional random fields, and another book which I have on my shelf which is the master book of probabilistic graphical models is called Probabilistic Graphical Models. It's by Daphne Koller and Friedman as well. Bayesian networks are very powerful tool to express and tell causal stories. So you see an example here, but you've seen already some examples in the previous slide. We'll be speaking about random variables in their relationships, directed relationships. So you see here, we have different variables, X, Y, Z, and Y, and we have a relationship. So we're saying here that X will have two effects, and Z will have one effect. So essentially, this is a compact way to represent highly dimensional joint distributions, because these are four random variables. They have a four-dimensional joint distribution, but the fact that they're linked to causal arrows makes us do some certain simplifications in the joint probability of these four variables have certain properties that we can read in a topological way from the graph. For example, I can immediately say that X and W are independent given Z. So Z is a screening node, and which means that given Z, the partial correlation between X and W is zero, okay, to use the economists' language of vanishing partial correlations. So there are many rules that help us read conditional independencies from the graph. Next slide, Olav. Why choose causal models and not correlation? So if you're working in finance, you know, for example, that to calculate your market risk, you use value at risk, okay, which is essentially measuring correlation between assets in doing perhaps a Monte Carlo simulation over the simulation horizon, which is usually 10 days for market risk. And this is a correlation approach. You see how assets have moved together and you assume this is going to hold in the future. You don't understand what caused those assets to move in that way. You just measure as opposed to understanding. And you just do a projection in your Monte Carlo and you assume that the future is going to be unlike the past. But that's not very robust because you don't understand markets in that way. If you use causal models, you understand, or you're trying to embed in your model the mechanisms that drive markets. Can be many events, can be geopolitical events, can be some endogenous things that happen in markets, but causal models, they have the property of being robust because you model really the underlying relationships between variables in the economy and markets, as opposed to just measuring them through a correlation matrix. So you inject your structural understanding in these models. They're easy to respond to changes, and we know we live in a very fast-paced world. Responding quickly to changes is essential. Instead of recalibrating complex econometric models, thousands of variables, like the common dynamic stochastic general equilibrium model. Here, with causal models, with Bayesian networks, you are really reactive. They allow to extrapolate beyond the past, and especially with regards to events that never happened in the past. And there are many of them in the political realm. We see Brexit, we see Donald Trump elected, Biden elected. These are events that never happened in the past. So we cannot build a robust statistical estimator for things that happened once. But nevertheless, we need to model. And we model them through injecting our causal understanding of how different variables are related together. And they're modular. I'll show you some examples, but if we need to replace, in layman terms, a part of the model with some new information, it can be done in a modular way without affecting the rest of the model. I'll give some examples. Olav, next slide, please. This is an example of a model that we built many years ago of how the capital account status of China and eventual China slowdown would impact on three asset classes, which you can see at the bottom, which is the foreign exchange between RMB and USD, house price index in China, and fixed income in RMB. And of course, there are other variables that intermediate the impact of eventual China slowdown on these asset classes. Specifically, we're speaking about the fiscal stimulus, the monetary policy of China, and the FX policy reserve. So you see there, these are variables, okay? Some of them we don't know how to estimate. We don't have history. So has China slowed down in the last 30, 40 years? Not really. So we want to model something that's unique, that potentially is about to happen. But again, we want to use a probabilistic language. So China will slow down eventually with a certain probability. So going to happen 100%. And all these things that you see here, all these nodes, these are random variables. So, for example, China could open their capital accounts with a certain probability. They could embark on fiscal stimulus with a certain probability. This fiscal stimulus could be successful or less successful to stabilize, for example, the housing market, which is given by the HPI variable. Okay. As Gauthier mentioned, this very much links to alternative data, because in order to calibrate this model, we need to populate them with parameters. And very frequently, alternative data is one of the means to do so. Next slide, Olav. Yes, so these models are embedded. They're embedded in a structure. So we speak about random variables and how they're related, but we need to populate them with parameters. We'll be speaking about discrete variables today, only about Boolean variables, but these models can accommodate many state variables, and they can accommodate continuous distributions. So continuous distributions might sound more complicated, but in reality, it's easier to work with continuous distributions. And when it comes to parameterization of these models, continuous distributions, they require fewer parameters than discrete models. In particular, the number of parameters grows exponentially with the number of nodes in a discrete network, while it grows quadratically in case of continuous variables. And of course, the expressive power of continuous variables is much richer, but it's always useful to start studying the discrete case. So we'll be speaking about Boolean variables. So here you see a cause A and a consequence B. What we need to provide here is probability of A happening and probability of B happening given A, the probability of B happening given non-A. So we need to provide three probabilities here. So sometimes it's easier to estimate conditional probabilities as opposed to pure marginal probabilities, like probability of A. And I can give you an example. So what is the probability of me finishing into hospital today? I cannot estimate it. It's a very difficult number. But what is the probability of me finishing in hospital if I'm hit by a car? Very high. So that I can estimate. So when you start building models, you start from a root cause, then you build down the tree. It's cognitively easier to estimate, to follow the direction of the tree and estimate conditional probabilities. So in this case, you see another network to the right. I have a cause A with two consequences, B and C. What we need to provide is probability of A happening, probability of B given that A has not happened, probability of B given that A has happened, and the same for C. So what do we do with this? Next slide, please, Olav. We can build different scenarios. So here I show very stylized, simple scenario, double dip recession, and how it's going to impact on Greece defaulting on their debt, on the UK equity market, and we have also another root event, UK downgrade. It's a very simple network. You see it's parsimonious. Not everything is connected to everything. In this case, instead of 15 parameters, we need just half of that number. Why 15? Because these are Boolean variables. In 2 to the 4th, they can assume 16 different states. So double dip recession could happen, UK downgrade could not happen, Greece default happens, UK market crash, but not happening. So you have different combinations. So you have 2 to the 4th, 16 minus 1, because probabilities must sum up to 1. So we have one closure relation. You can say it's not a big saving, but in big networks, you know, the saving of parameters can be several orders of magnitude. So this is a scenario. It was for looking at the time, so you can tell it was built around 2014, but now these things are not on the table maybe anymore. Greece being saved. But again, you understand the flexibility of building these simple causal models. Next slide, Olav. Yeah, the only formula that we'll be showing today. What do you do with these conditional probabilities? In the end, what you need to obtain is the master object, which is the joint probability table of these variables occurring in different combinations. So you can see one here to the right, and their probability. So this is the master formula. We take all the conditional probabilities that we assigned to the network and we glue them to a product. And from local objects, like the local conditional probabilities, we obtain a global object, which is the joint probability table of all the variables occurring. So here it's simple, 4 variables, just 16 rows. But for 10 variables, it's 2 to the 10, so 1024 rows. So it's very difficult to visualize it. But we took simple to assign probabilities, conditional probabilities, and we glue them together to obtain the object to the right. So we can see different combinations of the events happening in the probability. So what is the probability of A happening, B happening, C happening, and D happening? You can read it in row number 3. So it's 0.21%. But it's very difficult to estimate it. If one is asked the question, what is the probability of all these events happening? But we did local probabilities, conditional probabilities assignments. And by gluing them to this master formula, we obtain a joint probability table. So all this is stylized, but I can show you a real world example. Next slide, Olav. Please, yeah. So what do you do with this? So one application is scenario analysis, stress testing. If you plan for the future, yeah, you need to do stress testing, of course, in scenario analysis. Asset allocation, okay, under events that never happened in the past. So you want to know what's going to happen in the next election, maybe. You build a causal model of what are the relevant variables in this election, how it's going to play out, you know, and then you build a joint probability distribution. Once you have this object, you can do everything. So you can input it in your optimization engine, your portfolio optimizer, and derive an optimal portfolio under that scenario. But really infinite applications in scenario analysis and asset allocation, of course, and especially for events that never happened in the past. So I'll show you a realistic scenario that we built back in 2014 about the Scottish referendum. So this can be again on the table because Scotland is voting tomorrow, and if the SNP wins, they will call for another referendum. on Scotland independence. So this can be back on the table very soon. This one, I pull it out. But of course, the world has changed. Back in 2014, we didn't have Brexit. Now we had Brexit. So if there is another Scottish referendum, the context has changed. Hence the power of causal model, really to adapt to changing context. But how does it work in practice? How do you build these models? So a nice theory, you take random variables, you put them together, you model their relationship, you model probabilities. But in practice, how does it work? So you start always from a narrative. So it's just an extract from the narrative. Here, we think that if the vote is for independence, Scotland would take 50% of all reserves, 20% of the debt, will have to establish their own currency, their own regulators, and so on. So you always start from a rich narrative. And for us to build this scenario, we read around 50 different articles, papers, and studies. Next slide, please. Yeah, and we condense all these hundreds of pages of narrative into that causal graph. Okay, so you see the Scottish referendum outcome. It has impact on the over-reserve, the debt, the currency, the establishment of new pension and other regulators at the time, costs of funds for Scotland. So in order to populate this model, we read many papers, of course. In each of the links you see here on the graph, there is a paper behind this. So you see causal models, they're graphical, Bayesian networks are graphical, and they allow the incorporation of complex narratives, and you immediately can see what affects what. So instead of reading 100 pages, you can go to the graph almost immediately. So they are a very compact way to represent complex narratives. But what can you do, of course? It's not just the structure, it's also about the numbers, okay? Next slide, Olav. Once you have the numbers behind it, this is a network you can see that's been embedded in a software. It's called Hugging. You can download the free version, but it allows you to drag and drop different variables to assign probability and automatically calculates the entire network. So you can see the marginal probabilities here. Let's say the Scottish GDP down, bottom left. So the probability of it remaining the same is 34%. The probability of going down is 65%. So the name of this tool is called Hugging, H-U-G-I-N. And Hugging Lite is the free version with some limitations. But if you like Python, there are Python libraries like libpgm, PyY, I think. You can Google PGM, Probabilistic Graphical Models, Python. So we have some good libraries and also books in Python. But remember, behind this, there is a joint probability distribution. Once you have the joint probability distribution, you can slice and dice and ask query. You know, what would happen, for example, let's take a variable here to the Scottish GDP if the variable to the right, Scottish Bank's equity, is down by 10%. Okay, you can perform these queries, or what if they don't establish new pension and other regulators? How this is going to impact the Scottish Bank's equity? You can perform different queries. It's easy. So computationally, it's very easy, up to 20 nodes. After that, it becomes more complicated. Next slide, Olav. And I'm almost done with my part. You can do inference. So you can instantiate variables. So imagine you have a joint probability distribution. You can ask what would happen to the rest of the variables if I set one of the variables to a certain level. Okay, and here we set up the Scottish GDP being down 100%. And if you observe upstream, all the probabilities have changed. Essentially, we're looking for an answer. If the Scottish GDP is down 100%, how does the world have to look like for that to happen? Okay, so you can perform all sorts of sensitivity analysis and queries. Next slide, Olav. Yes, cognitive, easy and coherent. So what I noticed that, you know, as opposed to many black box models, you know, even econometric models. If you take a structural vote vector autoregression model, which can be represented as a graphical model, by the way, but any kind of complex regression, nested regressions, it's very difficult for the board of an institution to understand them. But here, a scenario is feasible. You can perform stress testing, also reverse stress testing. I just showed you an example. You can instantiate one of the nodes and ask how the probability of the other nodes is affected by all this. The next slide, Olav, and I think it's my last slide. Oh no, it's the second to the last. Yeah, this is another scenario here. Breakup of the euro, so sovereign defaulting in Europe. How this looks, how it's going to impact the portfolio of credit, equity, and bonds. You can see the result of the scenario marginalized to the three asset classes. You can see to the right. So my portfolio is going to have these shocks with this kind of probability. You can see this to the right. But there's a big question here. So when we introduce these two, so Bayesian networks been around for a long time, actually. As I said before, 30 years. If you use Excel and you see this really annoying clipper to the right giving you suggestions, that's essentially a Bayesian networks. They've been used in fraud analysis, medical diagnosis to diagnose different diseases. There's a famous Bayesian network for medical diagnosis with 456 nodes. So it's a very big one. So they've been around also in language translation with probabilistic graphical models. They have many applications, but why not in finance? So this is a big question. So when we started working 10 years ago, we haven't seen an uptake since then. So the question is why? A variety of reasons. The machine learning, artificial intelligence community has been focused more on associational models, like deep learning, of course, is very powerful to find patterns. But when it comes to causality, deep learning is really agnostic. But a lot of time has been spent on these revolutionary models, I would say. But when it comes to causality, they're not able to distinguish between cause and effect. So this is why causality has been forgotten for the last 7-8 years. And also because, at least in the banking sector, financial institutions have settled for scenarios that are more econometric, and this was driven by regulators for a long time. So they settled for all methods. This is why the uptake has been limited. Next slide, Olav. And there are also other reasons. So the first reaction I would have when I look at this model, when I look at the Scottish referendum or the European breakup scenario, they're complex. So for the Scottish scenario, I employed an economist. On the UK, we work heavily 1 week to get that scenario because I'm not expert. For other more complex global scenarios, usually need 20, 30 different experts. So recently we did a scenario on Qatar, and I needed an expert on Iran, on Saudi Arabia, on Turkey, on Qatar, of course, and the US. So it's very difficult to find these experts, okay? Then there is also the modeling aspect. So what variables to include in the model? This also applies to more standard models. It's the variable selection problem. Even if you calibrate a linear regression, you have to select the variables that go in the inputs. But here is a little bit more complicated. How to structure the links between the variables? What kind of probability, what data to use to assign probabilities to the different relationships? So you see there is a lot of subjectivity. But that doesn't matter. In order for you to be forward-looking in model events that never happened in the past, for example, you need to be a little bit subjective. But it's very difficult to devise a process where you have hundreds of different experts helping you build these models in a matter of seconds. So the process has been the largest bottleneck. But for the rest, these are perfectly reasonable models, especially now with the alternative data revolution, I would say. We have plenty of information for all the probabilities behind it. And I was in a state of despair until 1 year ago, until I met Olav, Pierre from Causality Link. And they had a really brilliant idea. So why don't mine expert knowledge from the web, use NLP, extract causal statements from thousands of different authors that speak on the web every day, and combine this in a Bayesian network in an automatic way. So the web, of course, can provide a pool of thousands of experts, NLP allows to extract their opinions, what they write in news articles, in a quick and efficient way. And of course, this can be combined in a matter of seconds in a model. Instead of spending weeks to build one model, why not leverage wisdom of the crowds, thousands of experts who speak about the economy, about finance, about everything, use NLP, extract their knowledge, and put it together automatically in a matter of seconds in a Bayesian network. And I will hand over to Olav, who is the brain behind this methodology, who can walk us through the NLP part, how we collect the knowledge and how it's structured in a Bayesian network.
Thank you, Alexander. So we extract data from financial texts. And the real thing is that we parse all kind of financial texts. I'll come back to the sources of that. But finally, those texts end up in basically 4 files. And those 4 files are indicators, trends, events, and links. And so really the base of it is we read texts, we create structured information out of that. And every element in those files is a simple one recognition of an element in text. So that will be the basis of what is the input to the BN. And I'll describe those 4 files or those formats in order for you to understand what actually goes into the into the Bayesian net optimization. So first, the indicators are the most important. They're the mentions in the text, and basically what it is, it's a KPI, and I'll give examples, plus a co-referenced context, so we know exactly what we're talking about. Then an important part is we need to understand where this indicator is going. Is it going up or is it going down? Then for completeness, the platform that we use also extracts events. However, in the current Bayesian networks, we're not including events at the moment. And finally, we have a file format that shows all the causal links between indicators or events, if you will, but we won't be using them. So indicators. Say that we find an article that's titled S.T. Lauder, COVID to blame for a weak Q3, right? I mean, that's a very common title for an article. And somewhere down in this article, you find hair care sales rose double digits in Asia Pacific, where there was less pandemic related disruptions. Okay, so what can the NLP understand from this, or what do we extract, if you will? Right? It all starts with a KPI, right? So the question is, what is being talked about? Well, sales, that's what's being talked about. And in our system, we have a very large ontology of KPIs, and it's hierarchically organized. And that is very helpful because, you have many different, very small scale KPIs. I mean, sales is a big thing, obviously, but you have deliveries or other things that may result in very sparse data if you take those exact KPIs. The way we organized the ontology was hierarchically, so that we can basically automatically roll those sparse KPIs up to a larger volume of KPIs that more or less mean the same thing. They're not synonyms, so they're still recognized on the lowest level. However, we can speak about them in a higher level terms. So the first item that is extracted is the KPI. We know we extract sales. We know that sales is a part of revenue. But sales of what? I mean, if you have an NLP that tags sales, this is a KPI, that's great. But what do you know? Well, you need to understand the context. You need to co-reference the context. And from here, not from this particular sentence, but from the article, we capture the context of a company. Namely, we're talking about S.T. Lauder here. And Estee Lauder in the ontology is recognized as a company, and it has a gigs industry associated with it, and its lowest level is personal products. So that's something that is just collected automatically via the ontology, not necessarily from the text. However, here they're speaking about hair care, and hair care is recognized as a segment. So we understand it's the sales of hair care, and then a location is detected, which is Asia Pacific. So we create a very specific naming out of this, and the detailed naming would be Estee Lauder Sales Hair Care Asia. That would be specifying exactly the mention that we find in this sentence. And so that is the element that gets stored in this indicator file. In a higher level, we summarize this as Estee Lauder revenue. And now you start to see that if we mine a massive amount of financial text, many people will talk about Estee Lauder. Right? Many people, well, on a large scale, absolutely. On a micro scale, maybe there's not a lot of people that specifically write about Estee Lauder. But if you collect like 50,000 articles a day, there's a lot of different journalists that point to items of Estee Lauder, and they will discuss their sales, they'll discuss their revenue, their profit. They may point to different segments, they may point to different locations. And so we are capable of simply now going to this indicator file and say, show me all the mentions or all the times that Estee Lauder revenue has been mentioned, and we pull from that file maybe 5,000 different mentions in the last month. That's what we will summarize. Okay, so that's the indicator part, so we know what we're talking about. Then there's a trend part, and we believe that an indicator is interesting, right? I mean, people talk about Estee Lauder revenue, but then the question is, what happens to that, right? And rather than I would say the emotional sentiment, so people say, oh, I like it or I don't like it. That's really not what we really care for. We care for the choice of experts saying that this element has gone up, has gone down, or will go up, or will go down. So we're focusing on trends. Now, we believe that this is still some kind of a sentiment, because it's not emotional, but it's still a sentiment, because an expert can also choose to not choose sales as a subject to talk about, but maybe the profit or maybe the demand for those products. So in a way, the choice of the KPI and the choice of what is being said about still carries some kind of intelligence of the journalist. And the journalist who writes this article is also not keen on just putting his emotional label, oh, buy this or I like this, but he wants to basically explain to the world, I understand this subject and I want to look smart. So we basically assume that this person is doing its best to come with a true statement that is insightful and intelligent. Now, of course, there's exceptions to that, but that is the mainstream. So when we find the trend, namely rows, we detect a number of properties for this trend. First of all, this is past tense. So we basically understand that they're talking about something that already happened. And the offset is measured to when it happened. Now, there's no, I'll give a clear example of what this offset is later in the next slide, but here there's no reference to when the sales actually rose. Finally, the word rose by itself, how many percent did it actually rise, right? Well, double digits. And that's not something that is clear. Is that 20%? Is that 10%? So we basically have a library that assigns an estimated value to those words. So double digits is 10%. If it would be, if double digits would not be there and it says haircare sales rose, then it would be 5%. If the sentence would say sales rose by 3.5%, we would pick up this 3.5% and then the estimated flag would be false because we actually pick up the number rather than we estimate it from text. All right. So let's go to another trend example, right? So and in 2020, October 7, there's an article appears and it says Musk said at the company's battery technology day that the full year deliveries should grow 30 to 40% year over year. Well, again, we start extracting the mention, right? So we start, what is the KPI? Well, the KPI is deliveries. Deliveries is something that adds up to sales, or that rolls up to sales in our ontology. And again, sales rolls up to revenue. So what is the context? Well, from slightly earlier in the text, we realized that this was the text was about Tesla, right? So and so we know that the company they're talking about is Tesla. We understand the industry of that, and so the detailed KPI would be Tesla deliveries, and the high level naming of this would be Tesla revenue. So that naming, you'll see that back later in the Bayesian nets. Hence, I go in detail about how this is being named. Now, the trend here says grow, right? So it grows, it goes up. However, the tense is future. And we have quite a capable NLP. And so if it says should grow year over year to the full year, we basically realize that the statement is made about the future and it's being actuated at year end. So if this statement, this actually appeared 7 October 2020, and our NLP automatically then computes that to year end is another 86 days. And so the offset here will be 86 days. So the offset is the number of days these events will happen in the future, or this KPI will be actuated in the future, or happened in the past, in which case it will be negative, right? If someone would say last week, blah, blah happened, then the offset would be -7. So the trend here is plus 35%. We simply take the midpoint and we capture the min and the max of that range. And is it estimated? It's false because we grabbed it from text directly. All right, so with that, I guess you have enough idea to understand. We capture the indicator, we capture a trend. Now let's look at the links. And if we find something in text that says, for example, wholesale inflation fell 0.2% in December, driven by lower gasoline prices. Well, that is a causal statement. That is someone who describes the state of the world and describes a causal link between those two items. And this is very interesting. And as exactly as Alex mentioned before, very often if you build a Bayesian net, you basically start to collect knowledge of experts. And you ask, well, we want to include inflation in our network. What is it driven by? And then the expert would say, well, look, one important component is gasoline prices, and they will have to kind of specify that relation. So instead, we basically get this quote unquote for free after the NLP is done, of course, because there's thousands of experts worldwide that describe these kind of relations. Now, we look at this again as a mention and a trend. but now we have a source part and a target part, right? So the source here, the KPI is prices, and with prices of what? Well, it's basically the price of an industry, and the industry here is oil, gas, and consumable fuels. The trend here is down, and for the target, we have inflation. This is actually, the location is not mentioned in this statement, but a little up in the text, it became clear that the context for this statement is the USA. So it's the US inflation, and the trend for this is down, right? So the inflation fell. At the end of the day, we get two indicators here that are now linked, namely the oil, gas, consumable fuel prices and the USA inflation rate, and the impact is positive, right? Because if the one goes down, the other goes down. Or if the one goes up, the other goes up, according to this author. Now, you might think, okay, isn't that always the case? Because if the gasoline prices go up, inflation goes up. That's just almost a law. Well, interestingly enough, that is not what authors describe always, right? So here we see in June, we saw an inflation slowdown despite the spike in gasoline prices. And the word here that's of interest is despite, because it basically shows that the author is kind of understanding that gasoline prices normally are positively related to inflation. However, now he saw something else. He saw, well, we saw an inflation slowdown despite that spike. And again, if we extract the elements, we have the prices of oil, the trend here is up, and for the target, we have the USA inflation rate, and that's down. So those are link statements. And if we now think back of those files, let me go to the next slide. We in the middle, you see those databases, the indicators, the trends, the events, and the links. Now, this is being filled, if you will, with 50K news articles per day across the world. It's automatically translated from 27 languages. And so you can imagine that's a massive amount of information. You see the number of detections that we have in our data lake below the table. So indicators that it's 642 million detections. So such things as Estee Lauder revenue, right? That would be a detection. The links would be the combination of the source and the target, that exact extraction from text. That is one element in that table. Now, in order to create a Bayesian net out of that, there's basically a few steps in between. The start is that from those base tables, we do SQL queries. And this all happens in AWS, and we extract those queries are done in Athena, which is a distributed SQL architecture. It's surprisingly fast. So I do a query and maybe 10, 20 seconds later, across this number of observations, I get a table. So for the links, I basically say, select the date, the source key, and the target key, right? The cause and the consequence, the strength, right? What was the link between those for the cases where the target key is inflation rate. And that gives me a link of individual mentions where the target key, where the consequence was US inflation rate, and where many different causes can be mentioned. So someone may mention the oil price, someone else mentions the food price, someone else mentions the GDP of Uganda. I mean, it can be there because someone can just write that, how the GDP of Uganda impacts the USA inflation rate. However, that last example will not be there that frequently. So with those individual statements, we basically aggregate those to the level of the source key and the target key, and we count. And then we take the top, for example, 5 predictors, if you will, or causes for a USA inflation rate. And we have a procedure to create a DAG out of that, the direct acyclic graph. So why is it a DAG, or why do we specifically need a DAG for that? Well, because in a way, nothing prevents people to say that the USA inflation rate also impacts the oil price, right? So that means the oil price impacts the inflation rate impacts the oil price, which both can be true. However, for the Bayesian net, we need an acyclic graph, meaning there's no cycles in any way. So the DAG algorithm is actually very simple. It's we take the highest frequency link, we add that to the graph, and we test if it's still a DAG. If that's the case, we take the next high frequency link, we add it to the graph, and if that were to kind of create a loop, we omit that link and we go to the next until we have decided that the number of links is sufficient in the graph. After that, the Bayesian net optimization happens. And so what we're doing here is described in detail of the paper, but essentially it comes down to, we're looking at how many times people were mentioning that the relation was either up, up, or down, down, right? So the cause is up, the consequence is up, the cause is down, the consequence is down. That is the positive relationship versus the opposite, the negative relationship, right? The case where people say, well, this went up and the other element went down. And we have seen the example for the oil price. You most would expect somehow if the oil price goes up, the inflation rate goes up. Nevertheless, there are enough people that describe the opposite, say, oh, the inflation slowed down despite the oil prices increasing. Finally, in this Bayesian net optimization, we basically learn or estimate the links automatically from text, the links in the Bayesian network. Finally, from the trends file, we select all the future or the forward-looking statements. And it's, again, a simple SQL file that says, SQL query that says select the date, the concept key, the item we're talking about, from trends where the offset is larger than 0 and the concept key can be oil price. That gives us a list of all the future statements of oil price. So people say, oh, we believe that the oil price will go up, or next month we expect the oil price will be up by la. And so we aggregate those statements into a number that says, what is the percentage of people or of statements that says that the oil price will go up? And that is what we will plug into the oil price. And then the Bayesian net automatically computes using the links that were estimated from the previous procedure, what the impact is on the food prices, the GDP, and the inflation rate. All right, so with that, hopefully you have some idea on how this works. Let's look at 2 examples. And the way to understand this net, and Alexander also mentioned that it's basically a complex story that's condensed in a very easy to observe net. However, the story is still complex. We have a specific way, we developed a specific way to display the networks. And you're seeing basically red arrows and green arrows. The red arrow indicates a negative relationship. saying that if the DXY, which is the dollar, the index of the dollar, or a basket of the dollar against a basket of other currencies, if the DXY goes up, metal and mining prices will go down. Or reversely, if the DXY goes down, the metal and mining prices will go up. Well, that somehow makes sense, right? We also see how the DXY has a negative impact on the gold price, which also makes sense, because if the DXY goes up, the gold price goes down. It's also interesting to observe that this is not the other way around, right? It's not the gold price that impacts the dollar, it's the dollar that impacts the gold price. Then we see how metal and mining prices has a positive effect on the gold price. So if the metal and mining prices as the industry, those prices go up, then the gold price will go up as well. So you can basically start inspecting each and every link in the graph this is automatically generated, and then start to decide, does this make sense? And we see thicker links, right? For example, the demand for oil has a very strong relation to the food prices. Well, that somehow that we understand that makes sense. And this link is thick, while, for example, the link between the oil production and the inflation rate is much thinner. So that is a weaker relation. So this display enables you to very quickly understand the different relations that are at play, which relations are stronger, and what is the directionality of that relation. Once we have inspected that, somehow we want to understand the bigger picture of this. And the bigger picture of this is look at the joint probability distribution as described by Alexander earlier. Now, in this case, what we show here is a graph, is a chart from the paper where we marginalize the bigger Bayesian net to the three variables of interest, namely the gold price, the oil price, and the inflation rate. And we added more and more drivers, saying like, show us a Bayesian network where the USA inflation rate is driven by the top 2 drivers, by the top 3 drivers, by the top 4 drivers, etc. We see that if we grow the model, the probabilities do not change very much anymore, which is a great example, which is a great showcase for the stability of those models. And it basically demonstrates that even with the smaller models, you have a good way to express the probability. It won't change a lot when your models become much larger. Now, as for the most possible, most likely scenarios, we basically see that the scenario for where gold price, oil price, and the inflation rate are all down or are all up are the most likely scenarios. And somehow we understand that because gold price, oil price, and inflation rate are all linked. So it's likely that they are either all up or all down, but they have a lesser chance of one being up while the rest is down, or vice versa. All right, so I want to conclude with one graph that is not part of the paper, or 2 graphs that's not part of the paper, but nevertheless, I think it's interesting to discuss this. This is something we recently created basically after the paper, and it shows how we can build those Bayesian networks over time. And we can do this on an hourly level, if you will, but of course that will be a lot of Bayesian networks to observe. Here I just took 2 time points, one of January 1, where still Trump was in play, and here one in April 1, where Biden clearly took office. And we see some very interesting things. So first of all, in January 1, no one was talking about taxes really, right? They said like, well, taxes will go down. And they said like, well, if the GDP goes up, right, the taxes will go up. So basically this is a natural relation. However, after Biden took office, people started to realize that the taxes would go up, right? And now suddenly the taxes will impact the USA GDP, but in a negative way, because if the taxes go up, you'll start to say, oh, that is bad for the GDP. Another interesting thing is that in January 1, the oil demand wasn't that high yet. But with a starting economy, we see that the oil demand of the starting economy after the COVID waves, we start that the demand for oil is actually being up, and that has a much better market as a result. And also we see that the prices will go up. Now that will drive the inflation rate. So if you compare the probability of the inflation rate being up from January 1, 67%, to April 1, 84%, we indeed see that the inflation rate is expected to be up or to go up. That also drives the USA inflation rate. So the USA inflation rate here was 47%. Now it's, sorry, the interest rate. So the US, it's now expected, or as of April 1, that the probability that the USA interest rate will go up is 70%, which is much higher than before. And it's also interesting to notice that in January 1, no one made a link between the USA interest rate and the capital market risk. However, that discussion suddenly started to appear, and we see a positive link between the USA interest rate and the capital market risk in April 1, as to say, if the interest rate goes up, then the risk in capital market goes up. So with this, I want to conclude and say, we believe that it's actually very interesting that we're capable of automatically extracting all those causal statements from text, from thousands of authors across millions of financial texts, and then automatically kind of create an image, a very condensed image of the state of the world, or of the state of the variables of interest in a smaller sense, and show how that changes over time, and basically use that as a monitor to fine-tune our understanding of the world. Let's see. With that, I'm at the end of my presentation, so I would like to open up for questions.